So we're back here with the CCEA Physics paper, Unit 1 from 2021. This is Part 2. We did questions 1 to 5 in Part 1 and you'll find that video elsewhere. So let's get started. Question 6 then. The magnets used in the Large Hadron Collider at CERN need to be superconducting. Explain the meaning of the term superconducting. So we need to explain that a material may lose all of its resistivity once it's put down to a temperature below what we call the transition temperature. So resistance falls to zero once we're under the transition temperature. Recently, researchers at CERN built a 40-meter long magnesium diboride cable capable of carrying a current of 20 kiloamps. Magnesium diboride has a critical temperature of minus 234 degrees C. On the axes shown in figure 6.1, sketch a graph to show how the resistance of the magnesium diboride varies with temperature in kelvins from 0K to 200K. Mark clearly the value of the critical temperature in Kelvin. So two things going on here. One, you're drawing the superconducting graph. The other one, you're doing a conversion from degrees C into Kelvin. Now you could just say 273 minus 234 is 39, but technically we're subtracting the lower number, which is minus 273, from the higher number, which is the minus 234. So minus 234 minus negative 273 gives us 39. And so the value we want to put on the graph axis is 39 kelvins. That's the transition temperature. And so for any value below that, we have a resistance of nothing. And then at that temperature, the resistance goes back to its normal. And then previous to that, we had a decreasing resistance. So our graph should look something like that. And this bit should probably be sort of vertical. I haven't drawn it quite vertical, so we should try and draw it as vertical as we can. There's very much a cliff edge in the value. So it looked like it was just heading down towards some final value at 0 degrees, but then we hit the transition temperature and the resistance vanishes. That's the crucial thing about a superconducting material. It disappears completely at a specific value of temperature. Part 2 then. Calculate the number of electrons which pass a point within this cable in 2 seconds when the current is 20 kiloamps. Okay, so 2 seconds. This is clearly like a Q equals IT question, and then we figure out how many electrons that represents. Okay, so we've got a time there of 2 seconds. We've got a current of 20,000 amps. We should be able to do Q equals IT for that. So 20,000 amps times 2 seconds will give us 40,000 coulombs. And what we want to do now is divide that by the charge on a single electron to see how many times an electron goes into it, and that will give us the total number of electrons present in that charge. So 40,000 coulombs on the top line. The electron charge, 1.6 times 10 to the minus 19 on the bottom line, will tell us how many we've got. And so we end up with 2.5 times 10 to the 23 electrons. So part 3 then, the number of particles in 1 mole is called Avogadro's number, n sub a. It has a value of 6.02 times 10 to the 23. Calculate what percentage of a mole of electrons pass a point every 2 seconds. So we're 2 seconds still, so we're using multiplying by 100. Go, but we'll do it in 2 parts. So we've got 15 kiloamps, 15,000 amps squared times 1.5 times 10 to the minus 6 to give us our 1.5 micro ohms. Put that through our calculator. 337.5 watts, and then we do power times time on that. And we get 20250 joules. Now all our input numbers are only to 2 significant figures, so we should quote that to 2 significant figures. So 20,000 joules, or 2 times 10 to the 4 joules, whichever way you want to write it. Seven starts with a nice easy bit. Again, define the moment of a force about a point. So make sure you refer to the point and the perpendicular distance of the force from that point. Part B then, a lorry can be fitted with a crane to deliver bricks onto a building site as shown in figure 7.1. I'm sure you've seen these things. They have a sort of little crane mounted just behind the cab that can lift stuff off the back of the lorry. The lorry has a mass of 3,500 kilograms and its center of gravity is 2 meters from the edge of the front wheels as shown. The arm of the crane is a uniform piece of metal of mass 400 kilograms and length 10 meters. So again, they tell us uniform so that we can locate the weight of that beam. Okay, the arm, because it's uniform, will have its center of gravity in the middle, and therefore we can represent the weight of that part of the crane acting down from the middle of that. So when they tell us that this is uniform, that allows us to work out that this must be 5 out, where the weight of the boom of the crane acts. Okay. Using the principle of moments, calculate the maximum mass of bricks which can be lifted by this lorry without it tipping. So that will be a downward force acting here. Okay. So again, we know that this is 10. We should add that this is 5. And we should also identify that if the lorry is going to tip, this point here will become the pivot. So we have to identify that as the pivot. Now if we redraw this as a simple moments problem with our pivot here, we can then add in all the forces on how far they are from the pivot. So the weight of the lorry is 2 meters from the pivot. Now if we continue this up here, the weight of the crane is going to be, well, this is going to be 5, okay, which means that this is going to be 3 from the pivot. And the weight of the bricks, which will act here, the weight of the bricks is going to be 10 meters out, but it's going to be 7 meters from the pivot. Okay, so we've got 2 meters to the weight of the lorry. We've got 7 meters out to here, and we've got 3 meters out to here. Okay, so we've got a force acting down here, force acting out here, and always we want to redraw, which measures how far everything is to the pivot. So you should take time to draw this and confirm that these are all the distances from the pivot after you've identified the location of the pivot. So the location of the pivot is crucial to getting this diagram right, and then all these distances. Okay, so although this is out up here, we've got 10 and 5, they are not the distance from the pivot because the pivot is already 2 meters out here. Okay, so I also can't count because that should be an 8, shouldn't it? Okay, so again, this is why you should get this thing right, because that's going to be an 8. Yeah, so 2 plus 8 equals 10. So that's 8 meters out. And this is where the weight of the brick sits. This is where the weight of the crane sits, and we've already got the weight of the lorry on it. Okay, so we want to add values to this. So the weight of the bricks we don't know. The weight of the crane we know is 400 kilograms. So we can write that as 400 times G. And we can write the weight of the lorry is 3,500, 3500 times G, W equals mg. And that'll save us having to put G into the numbers, because G will come back out of the numbers again when we calculate this final mass. So we're not trying to find a force, so G will divide itself back out at the end. You don't have to do it that way, but it sort of makes it a bit neater. Okay, so we want to write a moments problem for this. With our this is trying to push it anti-clockwise, this is trying to push it anti-clockwise, this is trying to push it clockwise. So we want to write a moments problem. And again, what I would do is identify the pivot with a symbol that we can then write a symbols version of our moments calculation, principle of moments. So the total anti-clockwise moment about P equals the total clockwise moment about P. The anti-clockwise moment consists of WB times 8 added to WC times 3, so that's 400G times 3. And they're equal to the total clockwise moment, which is WL times 2, which is 3,500G times 2. So we end up with like 8WB equals 1200G, or sorry, 8WB plus 1200G equals 7000G. So we need to subtract 1200G from both sides and then divide by 8. And that gives us 725G. Now that's the weight of B. To get the mass of B, we divide by G, which will make that G disappear, and we'll get 725 kilograms. So WB over G is 725G over G, which is just 725. So that brings it back to kilograms nice and neatly, without any 9.81s giving us all sorts of extra digits that we then had to iron out with our significant figures. So this crane apparently can lift 725 kilograms worth of bricks before it risks toppling. To enable the lorry to lift a heavier load than calculated in Part B, stabilizers are deployed as shown in Figure 7.2. Explain how these stabilizers function in order to allow the heavier load to be lifted. And you can see what has happened. We have basically moved the pivot out. The pivot was here at the edge of the wheel. Now it's moved out to here. So that's going to shorten the distances to the weight of the crane and the weight of the bricks, while simultaneously increasing the distance to the weight of the lorry. So the lorry's going to have a bigger moment, and the crane boom and the bricks are going to have a smaller moment, and that's really what you want to get down to in your description. So you're moving the pivot, that increases the moment of the lorry and decreases the moment of the bricks and the weight of the crane. And it does no harm to add to your diagram showing that you recognize that the pivot has moved with the addition of these stabilizers. So you want to make sure your statement covers all the bases. You're increasing the moment of the lorry, and you're simultaneously decreasing the moment created by the crane boom and the bricks. And so that change, and you want to specifically say that you're moving the pivot further from the center of gravity of the lorry and closer to the bricks and the crane boom. So something along those lines, trying to make sure that you've explained every aspect of it. Question 8 then. A student is provided with 1.5 meters length of constant resistance wire and asked to determine its resistivity. In the space below, draw the circuit diagram the student would construct, including an ammeter and voltmeter, to obtain a value for the resistance of the wire. So you need to draw a basic voltmeter ammeter circuit with the ammeter in series with the sample of wire and the voltmeter in parallel with it. So, you're not going to get points for artistic impression. There are only 2 marks. What they're going to be looking for is that the ammeter is in series with the wire sample and the voltmeter is in parallel with it. State an additional measurement that the student would need to make in order to obtain a value for the resistivity of the wire. So at this point you need to think about, what properties do I need to find the resistivity of the wire. Okay, so we've got the length there. This circuit will give us a resistance. So the other thing we would need is the cross-sectional area. So we would need to get a diameter in order to do that, and we would use an appropriate piece of equipment for that, something like a micrometer screw gauge. Part B, the resistivity value of the 1.5 meter length the student was provided with was 49.0 times 10 to the minus 8 ohm meter and had a resistance value of 12 ohms. Calculate the diameter of the wire under investigation. Give your answer in millimeters. Okay, so we need to put some equations together. So R equals rho L over A, and A can be found from the diameter So subbing in for your elements of that equation, your rho value of 49 times 10 to the minus 8, your L value of 1.5 meters, and your resistance value of 12 ohms should give us an A. So put that through your calculator. So we get 6.125 times 10 to the minus 8, and that's going to be a value in meters squared. And now we work backwards to D from the second equation. So if A equals pi D squared over 4, then D is going to equal 4A over pi, and then the square root of that. So we sub into that. So we have D at 2.79 times 10 to the minus 4 of a meter. We need to write that in millimeters now, okay? So if you remember, there's 1,000 millimeters in a meter. So there are 1,000 squared millimeters squared. What am I talking about? This is a linear thing, so we divide by 1,000, or multiply, sorry, by 1,000. So yeah, sorry for going off on one there. We've got a straight distance here. It's not an area thing anymore. Sorry. So we've got distance at 2.79 times 10 to the minus 4 of a meter, and that gives us a diameter of 0.28 millimeters. Now, why am I losing a significant figure? Well, because two of our numbers are the two significant figures, so our answer is going to be limited by the significant figures in the input. So although this is quoted to 3, the answer is going to be limited by these two only being quoted to 2. Okay, so 0.28 of a millimeter. So the student then finds another sample of constant wire which is twice as long but 4 times the cross-sectional area. Determine the values of resistance and resistivity of this new sample. Okay, so I'm smelling trick question here, because if it's still constant, and that is a property of constant, okay, the resistance is a property of the object we've constructed, but the resistivity is a property of constant in itself. So if we haven't changed the material, we haven't changed the resistivity, but we will change by making it a different length and a different cross-sectional area. We will create a different resistance. So we start by looking at our equation. What we're saying is that we've multiplied L by 2 and we've multiplied A by 4. Okay, so the whole thing has been multiplied by 2 over 4, which is a half. So it'll be half the resistance that it had before. So the new resistance is going to be the old resistance, which was 12 times a half. Now you could do that in stages. You could multiply it by 2 first of all and then divide by 4, but really you're ending up doing the same thing. So the resistivity of constantin is a property of constantin, not the thing we made. So it stays the value they quoted to us, but the resistance now becomes 6 ohms. Question 9 then. State the principle of conservation of momentum. Okay, again, nice for them to give you a sort of a learnable thing, and this is why you should learn all your definitions, because when you learn your definitions you get all these free marks in the test. This definition is a classic. What is true and when is it true? Okay, so when objects collide, the total momentum before the collision equals the total momentum after the collision, and then you state that this is true if no external force is acting. Can you imagine like two objects falling under gravity and colliding? They will both have their momentum increased during the fall by gravity. So that's an example of two things colliding when an external force is acting. So, you know, the idea that the the total momentum of a closed system is constant. Well, that's not going to be true if there's an external force acting, because if the objects of the system are all accelerating, then you're going to get an increase in the total momentum of the system. Okay, so the total momentum before the collision equals the total momentum after the collision if no external force is acting. What is true? When is it true? In a game of pool, a cue ball has a mass of 95 grams and it's travelling to the left with a speed of 32 centimeters per second as shown. Calculate the momentum of the cue ball and state its units. So this is a straightforward plug-in to the equation. What you always get at A level if you're just plugging straight into an equation is there'll be a unit conversion. And so we have grams and centimeters per second. So, the momentum will only be in a standard unit if you use standard units going in. So if you want to write that as kilograms and meters per second, then you'll get an answer in kilogram meter per second. If you don't do that, then you'll have some sort of Frankenstein unit, so you need to think about that ahead of time. They're not telling you what unit to write it in, but they expect you to be able to write the unit. Okay, so you could write it in grams, centimeters per second, and that would be a valid unit. What they're asking you to do is recognize in this question that if you do write it in grams and centimeters per second, you're going to get gram centimeter per second, not kilogram meter per second. Okay, so you just need to be aware of that. I would really err on the side of just turning it into standard SI units before you do the calculation, and then you can write it in kilogram meter per second. So momentum equals mv, and we need to write that in standard units if we're going to write it in kilogram meter per second. So 0.095 of a kilogram times 0.32 of a meter per second, giving us 0.034 kilogram meter per second. Sorry, 0.0304 kilogram meter per second. So we would put that in as 0.03 or 030 if you want, and kilogram meter per second as our unit. And you can write it in gram centimeter per second. The mark scheme does allow for that, but I don't feel comfortable with it, so I'm going to write it in kilogram meter per second. So we're told that the cue ball then collides with another ball which has a mass of 125 grams travelling in the opposite direction with a speed of 16 centimeters per second as shown in figure 9.2. After the collision, the other ball rebounds with a speed of 14 centimeters per second to the left as shown in figure 9.3. Calculate the speed and state the direction of the cue ball after the collision. So we should give the value of the cue ball's velocity afterwards some kind of symbol. I've chosen VC. We should also decide on a direction to take to be positive. And the cue ball was originally travelling, as you can see there, to the left. And to be honest, it doesn't really matter, but I'm going to take to the right to be positive. It doesn't really matter. So we're taking to the right to be positive, and so we want to write an expression or for the total momentum before, in this before situation where they're traveling towards each other, and for the total momentum after in this second situation. Okay, so total momentum before is this, respecting that we're taking to the right to be positive. Total momentum after is this situation, respecting again that we're taking to the right to be positive. So our 125 gram ball is moving in the positive direction. Our cue ball is initially moving in the negative direction. So we need to represent that when we write our equation out. So establish what you're doing. Total momentum before equals total momentum after. And then start filling in your values. So we've got, and we can use grams and centimeters per second if we want. We just need to remember that anything coming out of this will come out in those units. And you can see they want the answer in centimeters per second, so it's fine to use those units if we want. Okay. So we've got mass times velocity for that 125. 125 times plus 16, and we've got 95 for the cue ball times minus 32. And on the other side, the 125 gram ball is now moving in the negative direction. So we've got 125 times minus 14 added to 95 VC. So we bring those momentum terms, the ones that we have total values for, all together to one side, and then divide by the 95 to get VC. So you want to be careful putting that through your calculator because of all the negatives and things that are present there. You might prefer to take an extra line, just work out what each one of those values is before you put them all together over the 95. And that gives me positive 7.47 centimeters per second, which tells me that the cue ball ends up going in our positive direction, which is to the right. Part 3. State whether the collision of the pool balls is considered to be elastic or inelastic. Explain your choice by means of suitable calculations. So remember, an elastic collision is one where the kinetic energy is conserved. So what we have to do in this is find out the total kinetic energy before the collision, find out the total kinetic energy after the collision, and see if they're equal. Now, you could write this in like the Mickey Mouse grams and centimeter per second units, but if you want to write it in joules, you have to move everything to SI units, so you need to be using kilograms and meter per second to write joules, and I think I would prefer to do that. So it's a half times the mass times V squared for the 0.125 kilogram object and the 0.095 kilogram object. So that'll give us the total kinetic energy before. So a half times the mass of one ball times its velocity squared, half times the mass of the other ball times its velocity squared. Remember that we're in scalar world here. It doesn't matter the directions or anything here. We're just adding the values up. Okay, so we get that many joules for the before, and now we just do the same thing for the after. So we have to fill in our 7.5 centimeters per second value from the first part of the question, or the previous part of the question, and so we need to pump that through our calculator and see how much kinetic energy there was after the collision, and we get this much lower value. So we've had a loss of kinetic energy, so it's definitely not elastic. So we just state that then we've got a clear loss of kinetic, therefore it's not conserved, therefore we have not got an elastic collision here. So it's inelastic. So they say state whether it's elastic or inelastic, so you should make a statement about it being inelastic, just to finish it off. And that's us. Thanks for watching.